I think we are ready for the second part, and I will start with showing you some examples of functions for which we can bound the frequency. My first example is elementary, very simple, it's polynomials. If I take harmonic polynomials, of degree bounded by n, then my formula for the frequency, any of those, tells you that the frequency is bounded by 2 times n. If you don't like the formula, you can also think we believe that it's monotone on a very large scale. Our polynomial is like homogeneous of the largest order, and so it's bounded by this one. Our second example is a bit more interesting, and it will require some work. We'll start with a smooth bounded domain in Rd. And we'll look at eigenfunctions of the Dirichlet-Laplace operator on this domain. It's bounded. There is a discrete specter for this problem. There is the smallest eigenvalue that is positive. And what we will show that, in a sense, this function have frequency that is bounded by the spectral parameter, square root of the spectral parameter. But let me define this eigenfunction by phi. It is not a harmonic function yet, and I'm going to make a harmonic function out of it. It's standard lift. We add one more dimension, add the domain in Rd, and now we have a cylinder over this domain in Rd plus 1, and define the lift in this way. Then use a harmonic function To have my lambdas positive, I have to put minus there. If you integrate Laplace with phi and do integration by parts, you will see that the eigenvalues are negative. So then this is a harmonic function in omega times r. And for this harmonic function, we will show that the frequency of u is bounded by constant square root of lambda. The constant depends on omega. And say r is small enough. This is one of the examples where I get a harmonic function that is 0 on part of the boundary. Actually, on the whole boundary of this domain, but this is an unbounded domain, on this cylinder, my function is 0. So we can we can use our 3-sphere theorem on the boundary as well. So what I need to prove this claim, in the following statement, I have an R that depends only on the domain, such that on this scale, I have three-sphere inequality on each ball of radius R with center inside on the boundary. So X is an omega R. And sorry. So we have this inequality for any X there and R bounded by this R on small scales. There is an inequality like that. So to prove our claim, let us look at this function. And first I will note that if I have 2 points X, like that on this cylinder, if we just take a point and move it in the direction of the lost coordinate, nothing changes. My function is multiplied by exponential, and it's very easy to see that the whole average will be multiplied by exponential. So the frequency at point X of my function is the same as the frequency at point X1. Doesn't change from here to here. The average is multiplied by a constant. So it's enough to check this condition for the points that are on the original domain times 0. The last coordinate is 0. It's a nice smooth function there. Take the maximum of this function. There is a point where the function takes maximum. In the absolute value. And let us normalize our function so that this maximum is equal to 1. Then I know that the L2 norm over each ball is bounded, the average is bounded by 1. To bound the frequency, I want to show that the average over small balls are not too small. Right, then I'll be able to bound the frequency of the function using this inequality between the frequency and the log of the averages between over two balls. And to do that, we'll do very usual chain argument. We'll take a point x0 where the maximum is obtained, and a point, say x1, where we want to estimate our frequency, connect them in omega by a path, and have a chain of balls like that. So yeah, set that thing that the average is bounded by 1, but remember I don't want averages of my function phi, I want averages of function u. So if 1 is the maximum u of x here, then when I take a ball of radius, say 1, the maximum of the function is bounded by e to the power square root of lambda. So maximum of a large ball is bounded by this one, and I want to say that maximum of a small ball is not very small. And for this, I'm going to use this chain of balls between the point where there is a maximum and the point x1 where I want to estimate. Now it should be better. Right, okay. Yes, it's because I muted Mike while I was trying to adjust it. But now it's okay. Yeah. So we want to estimate the maximum function of a small ball and say that it's not very small. And for that, I want only to use this chain, saying that number of balls on this chain doesn't depend on my eigenfunction in any way. So I'll get some constant, but they are depending on the domain only, but not on the chain of balls. Sorry, but not on the function. Going to have the balls, all of them of the same radii, and such that the next one is a subset of a ball of radius 3 over 3/2 r. And then what we know is that supremum over bj plus 1 of u is bounded by the supremum of u over this ball three halves, and by our inequality it's bounded by constant times supremum bj to the power 1/3 times the supremum over some larger ball to the power 2/3, but say that my radius is less than 1, and supremum over the larger ball is bounded by e square root of lambda times 2/3. 1 is the maximum of the function. I multiply by this one, and if my balls are in the cylinder of heights 1, the factor is bounded by this one. So the next maximum is bounded by the previous maximum to some power times a constant. That depends on lambda here. And we do it many times, but the number of times we're doing it, it's the number of balls in our chain. It's a constant depending on the geometry of the domain and our R that we fixed. And what we get is the supremum over the last ball is bounded by C2 square root of lambda. When you iterate this inequalities, you'll get a large power e to large constant times square root of lambda, but it's something that is independent of lambda, this C2 times the supremum would be 1 u. And now I know which direction I want to go. I want to go from my ball where I want to get an estimate over the ball Bn where the maximum is obtained. So if I know that in the last ball there was a maximum of my function, this is larger than 1. I know that supremum over any ball of this radius R, it's not 1 over 3, it's now 1 over 3. And I guess that anyway, this n is once again number of balls in the chain, doesn't depend on lambda. What we get is supremum over function over B1 is bounded by e to minus large constant square root of lambda. So supremum over each ball is not small enough. It's bounded by this exponential. The L2 norm over a bit larger ball by elliptic estimate is also not small enough. So we conclude that the ratio between the average over this small ball and the larger ball where our function is bounded by square root of e to the power square root of lambda is bounded by this one. So this finishes the proof of the fact that for Dirichlet-Laplace eigenfunctions, if we take the lift, it's one of the examples of functions where we know that the frequency is bounded by constant times square root of the eigenvalue. I will mention one more example, but I'm not going to prove it. And the reason for that I don't know short proof, but probably you will think for a while and find one. So the third example that is still on the level of harmonic functions where we don't need to go to elliptic PDEs is the following. If once again we have a smooth bounded domain, and now we'll look at another eigenvalue problem. We want a function that is harmonic in the domain, but on the boundary it satisfies the following condition. The normal derivative is proportional to the function with coefficient sigma, and it's called Stiklov boundary problem, Stiklov eigenfunctions. Then we claim that for such functions, the frequency, whatever you write, is bounded by constant times the spectral parameter. So it's another family of functions for which you know how the frequency grows. Before we go further, I want to mention two things about this frequency. So we have some examples where we know that frequency is bounded. And what I want to explain that there is no way the frequency is bad everywhere. By bad, I mean large. My first remark is simple. Suppose that I have a ball and I'm going to cover it by small balls of a much smaller radii, equal ones. And suppose that I know the frequency function on each of these balls, and suppose they all are large. And then I claim that for this ball, the frequency is much larger. So U is a harmonic function defined in the union of all these balls. And we want to claim that the frequency is larger than constant, that is a large constant, times the maximum of the frequencies. Here, probably minus another large constant. So if we know that all these frequencies are large, the frequency on a large scale is much larger. It tells us that if our function comes from one of these examples when we know how to bound the frequency on a large scale, then at least at some portion the frequency is much smaller than what we expect.
Shouldn't be a minimum, the max?
Yes, thank you. Yes, if all of them are larger than this one is even larger. And the way to think of it is a simple, I will rewrite the frequency Remember, it's the ratio of it's roughly speaking, it's the log of the ratio of these ones. But once again, since we work with harmonic functions, we can estimate this by supremum norm over a smaller ball and supremum norm over this ball. So it's roughly speaking the log of the maximum. Squared. You can make it precise by using some inequalities and changing your ID a little bit, adding a constant there. So let me write plus minus constant, not to worry about that. And then if we have, say, this ball of radius r here, we will look at half of the ball and choose a point where our function u achieves the maximum on half of the ball. So let u of x is the maximum be x r over 2. This point is covered by one of our balls here. And x is in b xj r for some r. We know that the doubling for this ball is large. It means that if we have a point where the value is absolute value of u, and we take double ball, the value will be multiplied by, the maximum will be multiplied by 2 times the frequency. Let me call this maximum small m. If you want to make this precise, you'll need to probably take away a constant here. And I can repeat this procedure a few times, right? This first point was on ball of radius r over 2. And then I step away on distance small r, and I can do many steps here. So I can do k, that is approximately r over 2r steps before I reach the boundary of this large ball. And then we will see that the maximum of b xr u, it's at least 2 times constant, then this minimum of these frequencies minus constant m. So if all of them are large, much larger than this constant, then we get that on a large scale we have a huge frequency. This ratio of this maximum over ball and half a ball is approximately the frequency on this scale R. So the conclusion is that we have this inequality. And this is a simple remark that says that there is no way frequency is large everywhere. In fact, much more is true about the distribution of frequency. And I'll formulate one result today. That is due to Sasha-Logunov. And it's a very nice interpretation of the three-ball theorem in terms of the distribution of the frequency function. Suppose that we are in RD and we have say d+1 points in the unit ball that are vertices of a non-degenerate simplex. We'll assume that the minimum distance is large enough and this simplex is wide enough. Another way of thinking, if you play this simplex between two hyperplanes, the distance between these hyperplanes is large enough. Everything is on scale 1 more or less, so we have a simplex, we assume that it's not too thin, all the sides are scale 1. And then the conclusion is for any function harmonic in a big neighborhood of this ball, what you have is that the frequency of this function at the center of the simplex, this is the center mass of the simplex, for R that is quite large but not too large, this frequency is bounded. Sorry. I should subtract a constant, probably not. Let me subtract a constant just in case. So for large frequencies here, you get that the frequency at the center is even larger. So not only all the frequencies are not allowed to be large, but even just few of them are allowed to be large. I'm going to prove it. It's geometry plus 3 ball inequality, nothing else. Let me give you a non very honest sketch why this is true. Suppose that our dimension is 1. No one does harmonic functions in dimension 1, but suppose we are in dimension 1. We have center of mass and 2 points, say -1 and 1. And suppose I know that in both these points, the frequency or the doubling of my function is large enough. I want to show that when I'm centered at this point, the doubling is even larger. So let us look at the interval minus L minus 1, L plus 1. It is the union of two intervals, one centered at minus 1, another centered at 1. Let me do it in a different way. So interval at 0 of length L plus 1 is the union of the interval here and the interval there. Now, if I know that the doubling in each of them is large, take one where the maximum of my function is obtained and double it. And then we will see that the maximum is multiplied by 2 to the power, that is a frequency. What will happen to the intervals if I take the double intervals here? The union is an interval centered at 0 of the length 2L plus 1. So the length is not doubled, but you have this ratio is less than 2, and at the same time the maximum was multiplied by 2 times 2 to the power of the frequency. What happens here in high dimensions is almost the same, but you have to do a more careful geometric picture, and you can try to do it in dimension 2 and convince yourself that you can place a ball in the union of a ball centered at the vertices of a triangle with a smaller radii, multiply this radii by a constant, and you will have a larger ball where the ratio is less than the ratio of the radii of the small balls. So here my ratio was 2, but in the end I have a system of 2 intervals with ratio of lengths is less than 2. And you have the same geometric picture in high dimensions. Okay. It's a constant times, it's still a constant. It should be very large. If it's very large, then if my L is very large, this ratio is approximately 2. I don't gain anything. But there is a scale on which you actually gain things. Right, so it's, in my formulation, it's a constant. Not too large, not too small. Right, so the next thing that I wanted to mention is that it helps to think about functions with bounded frequency more or less as polynomials of the corresponding degree. We would like to know more about that, but it's still there are some examples of statements that you can extend from polynomials to this situation. And I'll start with a simple remark. I'm now in RD. I have a harmonic function in the unit ball, and I bound the frequency I'm on a simple level of harmonic functions, so I can write my function as harmonic polynomial of degree m plus the arrow term. And take this m larger than the frequency function. Use the definition of our frequency. What you'll get is that the arrow term, if we take the L2 norm over the sphere, it's bounded by L2 norm over the function that is normalizing coefficient, and then you have a factor that is something like that, that goes to 0 is 1 over m. What I place here is constant over m minus n. And this is a simple computation using the expansion of our function into the series. I don't know how to extend this to elliptic equations, what would be the right thing, but still, for elliptic equations, you can use the frequency to approximate it, for example, by harmonic function, and then approximate harmonic function by polynomials. I'm not going into that direction, so approximation of elliptic by harmonic is a nice topic, but I don't want to go into details over there. One way where this way of thinking was useful is the following lemma that is a joint work with Stefan, who's here. And it tells you that if you have harmonic function with this frequency, then you have the following version of Bernstein inequality. And we believe that this version is like that. So I will want my function to be harmonic in a bit larger ball. And I will want the frequency on this scale be bounded by n, and then the maximum of the gradient of the function over the ball of radius 1 is bounded by n log n maximum of the function be 0. This is kind of Bernstein inequality. In classical Bernstein inequality for polynomials on the interval, what you'll get is that the maximum of the derivative over 0, 1 is bounded by n squared times the maximum of the polynomial of 0, 1. But there is some version of this for eigenfunctions, was noted by Donald and Pfefferman, but in their work, the coefficient that you get here is a large power of the eigenvalue. What we believe is that you can go with not so large power of eigenvalue that doesn't depend on the dimension. And what you see here, it's in a way is better than that one. I have n log n instead of n squared, and it turns out, we believe that for harmonic polynomials, the thing is better. If you average a harmonic, not average, if you take the maximum of a harmonic polynomial over a ball, then instead of a degree squared, you have the degree here. And you go from harmonic to polynomials to harmonic functions, you get an extra log. And then you can try to go from harmonic functions to elliptic PDEs. Another statement about polynomials that we can generalize to solutions of elliptic PDEs with bounded frequencies, the following one. I will start with an inequality for polynomials of one variable. Suppose that we have an interval and a subset of positive measure on this interval. Then the maximum of the polynomial of degree n over the interval is bounded by the maximum over this set E times a factor. Let me see, let us normalize things so that the length of the polynomial is equal to 1. Then what we will have here is 2 over the length of the set, the measure of the set minus 1, and we compute the Chebyshev polynomial of degree n at this point. When E is of full length 1, then this coefficient is 1. When E has the same length of the interval, it's the whole interval, more or less, then you have a trivial inequality with the right coefficient. But you can also check that this bound is bounded by 4 over E to the power n. So the initial or premise inequality is better because this is easier to prove than this one. When this is a weaker statement, it's easier to prove that Chebyshev polynomials are actually the ones that give you the answer than to prove an abstract estimate like that. But it's also better because when E goes to the full thing, you have a coefficient that goes to 1 when n is fixed. Here, this coefficient blows like 4 to the power n. And what we know about this version of this for harmonic functions or elliptic PDEs is the following. If you have, say, harmonic function in the unit ball, with bounded frequency, take B to be a half ball and E subset that this has a positive measure. Now this is in dimensions D. The back measure is positive, then the maximum of U over closed ball B is bounded by a constant times, I can include this, length of the ratio of the volumes to the power constant times n plus 1 maximum. Surprisingly, to prove this, you don't need anything but just the fact that you already know. The monotonicity of the frequency plus the simple remark that frequency is not maximally large everywhere is enough to do induction on scales and prove this inequality. We would probably prefer to have something similar to this one, to have a factor that doesn't blow up when your set E goes to the whole ball, to have a more careful coefficient here that shows that if E is actually a large part of B, there is a small constant there, not a large constant. So if you think that this is extra, roughly speaking, if the measure of E is like that, you would expect this constant not to blow up, to be bounded. But we don't know how to do that. I think I should stop now because it's 10:03. I did almost everything I wanted to do today, and we will start to talk about critical sets tomorrow and try to estimate size of the critical set using the frequency of the function.